I'm NADIA FAWAZ, an applied scientist and the technical lead for inclusive AI at Pinterest. This work is the result of a cross-functional collaboration with many talented peers at Pinterest, as developing inclusive AI in the product requires a multidisciplinary approach, not just technical expertise. So I would like to start by sharing some feedback a pinner sent us a few years ago. She told us that to see people of color in our app, she needed to physically type the word black, and that looking at our app told her that people who looked like her were not the norm. Pinterest's vision is to bring everyone the inspiration to create a life they love, and to truly be a place where everyone can find the most inspiring and relevant content for them. Pinterest is committed to content diversity and to developing an inclusive experience on the platform. Over time, Pinterest has evolved from a visual discovery engine to an inspiration to realization platform. And because a picture is worth 1,000 words, I would like to show you a short 1-minute video clip to help you visualize Pinterest. Machine learning powers many advanced search and recommendation systems at Pinterest. And these systems tend to be very complex, and they have many components as they need to operate at the very large scale of over 400 million global monthly active users who have saved over 300 billion pins to more than 8 billion boards in over 35 languages. And we strive to be a place filled with positivity for pinners. Now, how do these systems work? In a nutshell, these systems consist of several machine learning models trained to optimize some objectives. For example, to predict the likelihood that a pin would be relevant to a pinner given inputs such as queries. And at Pinterest, data is multimodal, so queries can be in the form of text, such as the queries typed by the users. They can be visual, when users input an image to search, or they can be an entire pin. And a pin is more than one or more or multiple images or video. It has a title, a description, a creator, a link to a website. These models also take as input user features, such as interests that the pinner follows, content features, such as images, videos, and the description of the pin, and past interactions with pins and boards that have happened on the platform. So then pins are retrieved, ranked, and blended according to these predicted scores, and the list is surfaced to users in the app. Now, if the data we input in these systems is not diverse, the machine learning models may learn implicit biases, serve biased results in production, leading us to collect more biased data, and this is the creation of a bias feedback loop. We would like to move toward a virtuous cycle where we start with diverse data, we mitigate potential biases in the system, and we make the user experience more inclusive. The goal of the Inclusive AI team is to make our AI systems perform outstandingly well across our diverse sets of users, and that includes pinners, but also content providers such as creators and merchants for a wide range of use cases. Now, developing inclusive AI requires an end-to-end iterative and collaborative development approach. We have learned the importance of building inclusive systems by design, of measuring to make progress, and of leveraging both artificial and human intelligence. And we recognize that these challenges are multidisciplinary, not just technical. So we work within a large cross-functional team where engineers collaborate with people across the organization. In this presentation, we will discuss why it's important to reduce bias. We will review sources of bias in machine learning-based systems and techniques to mitigate these biases. And I will present production examples of inclusive search and recommendations we have developed and deployed at Pinterest. So why is it important to reduce bias? Mitigating biases allow us to move away from historical patterns of bias in society that are unacceptable. And poorly designed systems in risky applications can lead to harm. It also allows us to work ahead of regulation. Recently, both the European Union and the US Federal Trade Commission have started issuing guidance and drafts for AI regulation, including AI fairness. Another reason why reducing bias is important is to put users first. Users care about the quality of recommendations, and improving user representation and experience can lead to more engagement, improve exposure for content providers, creators and merchants, help grow in new markets, and help us retain our competitive advantage as a positive corner of the internet. And last but not least, there are technical reasons to reduce bias. It's part of good technical craftsmanship. A system that significantly underperforms on a segment of the data is not a high-performing system, and we would be leaving technical value on the table. AI fairness is a nascent area. We recently saw a sharp growth in research papers, but the number of companies that build change into their technology and product is still small. And so the work we're doing at Pinterest in products not only improves our user experience, but it also helps raise public awareness about algorithmic bias. And it can have an impact on how the technology industry develops technology and products. Now, what are sources of biases in machine learning-based recommender systems? Biases may arise at different stages in these systems. It starts with societal biases that are inherently present in the data before we do anything with it. So this table comes from a study by the Pew Research Center. It shows a mix of users according to their demographics in various online platforms. And when we look at this data, we realize that each platform has its own mix of users according to different diversity dimensions. Such a diverse set of users has an impact on the content available on the platform, but also on how users interact with this content. Now, there are many diversity dimensions. Common ones include demographic dimensions such as age or gender, but it can also be geographic or cultural dimensions such as country or language. Some dimensions are application specific, such as, for instance, hair pattern or skin tone for beauty. And sometimes the diversity dimensions cannot be expressed as a combination of explicit dimensions, but rather are implicit dimensions that need to be expressed using, for instance, latent representations. Now, biases can also be introduced by data collection process. Serving bias occurs when some examples are less likely to be included than others in the datasets. In production systems, feedback is collected based on the production model in place, and feedback can only be observed on items that are surfaced to the user. Position bias is due to users' propensity to pay more attention to results appearing at the top left corner of the page. Summary-based presentation bias happens as users may favor and click on items that they deem more attractive as per their visual or textual components. And repetitiveness bias is due to user fatigue when an item is repetitively surfaced to them. So in this graph, the click-through rate decreases the more an item is shown to a user. Biases can also come from the modeling choices we make. And I would like to make here a distinction between two types of biases. Statistical model bias may arise when the complexity of the model is not sufficient to fully represent the data. So imagine the data is generated by a quadratic, and we try to fit it with a line, The line will never fit the quadratic perfectly, even if you give it more of the same data. Some error will remain. This is the more modern version of this graph. Now, this type of bias is different from algorithmic bias in model fairness, which is concerned with mitigating disparities in performance for different groups according to a diversity dimension. Bias can come from an aggregate loss function that favors the majority or that is focused on a single utility. It can also come, for instance, from the structure of the system. If some components are biased, the bias may propagate to the system. And the way we tune some hyperparameters can also lead to bias. After data is collected and the model is trained, we perform offline evaluation of the model. This helps us to evaluate if the model can generalize to unseen data at training. And it also helps us to iterate fast on models before our productionization efforts. Offline evaluation allows to rule out models that did not perform well on offline data and avoid sending poor models to users in production. Biases in offline evaluation can happen if the data lacks diversity or proper coverage for all groups. And the performance might not be measured for some groups. The data may come from human labeling that may be biased, as each one of us has their own biases. The evaluation may be performed on static data, but the world has changed. And the evaluation metrics may be coarse aggregates that favor the majority class, such as, for instance, accuracy, and that hide poor performance on underrepresented groups. So I'd like to illustrate this in a toy example. So imagine there are two groups, one large and one small. And in group A, most people prefer apples. And in group B, most people prefer pears. And there is this imaginary algorithm that looks at past data, learns that red apples are the most popular fruit, and so it always recommends apples now. So what is this algorithm performance? Well, its overall accuracy is 74%. It may seem that it's doing okay. But is it fair? If we take a closer look at how it performs for each group, we see that there is a gap. Errors disproportionately affect a group. And mitigating bias disparities in performance between groups is the main focus of algorithmic fairness. Now that the data has been collected, the model has been trained and evaluated offline, we would like to start an experiment in production, an A/B test, and bias may come from how the experiment is run. So these graphs are from an experiment run by colleagues at Pinterest. The left graph shows the proportion of users in the experiment in three groups: core users, who engage frequently with the platform, casual users, who engage a little less, and marginal users. The distribution of users in this experiment changes over time. At the beginning, core users represent the largest proportion of users in the experiment, and then this proportion decreases as time passes and casual and marginal users have time to come in. The graph on the right shows how the lift of the new experience relative to the control evolves over time. At the beginning, when the core users are the largest proportion, the lift seems like a gain. But if we wait long enough for non-core users to appear, the lift eventually becomes a loss. And so too short experiments may lead to the wrong conclusion. Now that we have reviewed some of the sources of bias in these systems, we'd like to discuss which techniques can be used to reduce bias. So several techniques can help reduce bias at different stages of a machine learning system. One approach is to give control to users over their experience, such as, for instance, with inclusive filters. A top request we hear from pinners is that they want to feel represented in the product. So this is why we built the skin tone range and hair pattern search. These inclusive features enable pinners to narrow beauty and hair results by a skin tone range or hair pattern of their choice in search and AR try-on similar look recommendation module. And later in this talk, I will walk you through our journey to build these inclusive features. Another technique is diversification. Diversification approaches aim at re-ranking content to make the set of items that is surfaced more diverse by default. And I will describe it more in details in the later part on examples in production. A common way to address serving bias is through randomization techniques, such as top K randomization, that shuffles the top results before surfacing them to create an opportunity to observe feedback on lower ranking items that would otherwise not have been surfaced and we wouldn't have been able to collect feedback. But a more economical approach is to use explore-exploit techniques that alternate between two phases. An exploitation phase that selects items with high predicted scores according to the current model, and an exploration phase that takes an intelligent risk to serve items with lower predicted score and give a chance to collect feedback on them. And that helps the model learn in the long term. Data can also be augmented through diverse data labeling, data transformations, error collection, and negative samplings. And error patterns and the types of negatives that help the model learn may be different for different segments of the data. At the modeling stage, data can be pre-processed through sampling, upsampling or downsampling the minority or majority, reweighing the samples in the loss function, leveraging fairness-aware pre-processing. The modeling structure can also be revised through error analysis of the components, richer feature sets, ensembles, revised training objectives, and we can also add fairness constraints in the optimization and perform fairness-aware hyperparameter tuning. Now, offline evaluation should start with diverse data with coverage for all groups. Quantitative evaluation should go beyond aggregate metrics. Measuring granular metrics per group allows to quantify disparities and to mitigate algorithmic bias. And there are open source tools that support fairness metrics. Having humans in the loop is also invaluable in developing inclusive technology by integrating qualitative feedback from human evaluation, users, and communities. We've noticed that artificial and human intelligence are complementary, and leveraging both in development yields higher performance than either can achieve alone. And finally, diversity and fairness metrics should also be measured in production once the models have been developed and reevaluated over time. So I would like now to walk you through examples of inclusive AI developed and deployed in production at systems to build inclusive search and recommendations. So as I mentioned earlier, a top request we hear from pinners is that they want to feel represented in the product. So this is why we built the skin tone ranges and hair pattern search. These inclusive features give control to pinners on their experience in search and AR try-on by allowing them to narrow beauty and hair results by a skin tone range or hair pattern of their choice. So how did we build the skin tone ranges? I would like to walk you through this journey. In the early days, to understand the skin tone in a beauty image, we considered a third-party closed-box computer vision library. It was composed of several modules. It had a deep learning module for face detection, followed by a color extraction module. We got the LAB color coordinates, threshold on the lightness, and used that to estimate the skin tone range in a beauty image. So this was launched in production in 2018, and we heard positive feedback from our users who saw their experience improve. In particular, it became easier for them to find relevant content in the darker skin tone ranges. However, over time, we started noticing issues with the performance of the closed box version based on visual inspection. But in order to make progress, we needed to quantify the extent of the issue. So we collected a diverse data set that a specialist labeled, and we conducted an evaluation of the closed box system using this diverse data. We analyzed the error patterns and quantified the disparities in performance across different skin tone ranges. The confusion matrix here on the left revealed a major coverage issue for the closed box predictions in the darker range. We also noticed performance disparities in the granular precision, recall, and F1 score per skin tone range. In an image, at the top, the ground truth is a diverse set of beauty images labeled by a specialist, and the middle row shows how the closed box understands the skin tone for these images. And as you can notice, it has a coverage issue for images in the darker ranges, where the closed box cannot output any prediction. And it fails to understand the skin tone ranges accurately for many images. So to understand why this was happening, we conducted an error analysis of the components of the system. The top right corner shows the score distribution for each skin tone range. Those score distributions are not really separable, they overlap. And the thresholds are out of phase with the diverse data. And these type of issues can be amplified by shadows and challenging lighting conditions in the images. Then when we looked at the output of the face detection module, we realized that the coverage issue for darker skin tone ranges was coming from there, because the face detection module failed to detect faces for the darker range images at much higher rates than for the lighter skin tone images. And that type of bias in face detection technology has been studied and documented by Joy Bolamwini and Timnit Chebu in the gender shade study a few years ago. So we reached the conclusion that there was no amount of post-processing on the output of the closed box system that would fix these built-in biases in its components on which we did not have control. So we needed to build our own system end-to-end in-house, and that's what we did. In our first in-house version of the visual skin tone, we developed a system with several computer vision components. After exposure correction, it detected the location of a face in a beauty image, extracted facial landmarks such as the eyes, the nose, the mouth, segmented them out to output a skin mask. And in the case where the face was not detected, the hue saturation value module processing module allowed to detect patches of skin pixels in the image. The skin mask was then fed into a color extraction module. We generated the LAB color coordinates and computed the individual topology angle, which is a nonlinear function of those coordinates. And then we passed that into a fairness-aware tuning phase that took as input a diverse data set to finally output the skin tone range in the image. Now, when we evaluated the performance on the diverse data, it looked much better. The confusion matrix was closer to a diagonal and more symmetric. The score distributions were more separable, and the per class precision, recall, and F1 scores were not only higher for every class, but also the disparities between the classes had reduced, meaning that we had reduced bias in the performance. So back to this image. This is how it looks now. You've already seen the top and middle portions of the image. Now the bottom row shows how the in-house visual skin tone performs. We don't have the coverage issue anymore on the darker skin tone ranges. And while it is not perfect, we had made a lot of progress. Now this is not the end. Even the visual skin tone V1 could make errors. And we learned from these errors and made the model learn from them too. So let me share some examples of images that tripped the visual skin tone V1. Extreme lighting conditions were challenging. Occlusions such as beards and sunglasses can lead to errors. And then the pandemic happened. And as the world changed, so did images on Pinterest. The pandemic caused a surge in face mask images to which the model had to adapt. In some images, there are multiple faces or a combination of faces. In other images, the face is not visible or there's no face at all because we have other body parts. So these cases prompted us to search for a more robust approach. So first, we invested in collecting our largest and most diverse data set yet for skin tone. It included images from previous errors, partial faces and body parts to handle new use cases such as lips and nails, and new verticals such as beauty and fashion, and internationalization. And for the system to handle more complex images, we decided to move away from face detection entirely, and we experimented with different architectures. We first used an approach that learns the skin tone range directly from the raw image pixels using convolutional neural networks. So this ResNet outperformed our visual skin tone V1 when evaluated on this larger, more challenging data. Next, we leveraged the multitask visual embedding that the computer vision team at Pinterest developed. This unified visual embedding powers important visual search experiences at Pinterest, such as visual shopping and lens. So we added a skin tone classification task and used that to predict the skin tone ranges. And when we evaluated this approach on the more challenging data and some of the error cases I presented earlier, it outperformed face detection by a large margin across all metrics while performing similarly across genders. And so the improved skin tone model gave us the confidence to expand beyond beauty to the fashion use case and to make the skin tone ranges more prominent in the product. We built on our learning on developing skin tone ranges with bias mitigation to develop hair pattern search. Hair pattern search is powered also by a computer vision model trained on diverse data to understand the hair pattern that's visible in an image. To define the hair pattern categories, we consulted hair experts who work with Black, Indigenous, and people of color, including Naïma Lafont, a Pinterest creator and the global artistic director for Amica, a hair brand. Their guidance, the help of our beauty and fashion specialists, along with our user research team, informed our technical choices throughout development. And user research really played a crucial role end-to-end in building hair pattern search with inclusion at the heart of technical choices, from the ideation phase to design and development to evaluation of the production feature. To mitigate bias and ensure consistent performance of the AI model across different segments of Pinterest content, we collected a diverse set of hair images across hair patterns, skin tones, genders, and hair-related interests. We integrated hair pattern predictions into Pinterest's latest visual embedding multitask model that leverages state-of-the-art vision transformers and our investments in our computer vision infrastructure to scale to billions of images. And we iterated multiple times, incorporating feedback, augmenting the data, and retraining the model to make it learn from its errors. Today, the skin tone ranges power a more inclusive experience in 19 countries, and we launched hair pattern search in 15 countries. We worked with our internationalization team in local markets to evaluate and launch these inclusive experiences internationally. Our work on skin tone ranges and hair pattern search received global press coverage, and hair pattern search was recognized in the AI and data category on Fast Company's 2022 World-Changing Ideas list with an honorable mention. I'd like to share a few learnings from going on this journey of developing the skin tone ranges and hair pattern search. So first, I'd like to encourage you to start with diverse data, but also to remember that bias can come not only from the data, but from the modeling choices and the evaluation processes that we choose to use during development. It's important to test and test again the performance at every step of the system. This means testing every component within the system and testing at every stage of the development, during offline evaluation, A/B test experiments, and continuously monitoring in production. Evaluation should go beyond overall accuracy or other aggregate metrics, and quantifying biases and analyzing the error patterns at the granular level helps to iterate fast and to mitigate bias. It's important to learn from the errors the model makes and to make the machine learning model also learn from those errors. And building iteratively allowed us to uncover the complexity layers. These problems are complex and hard to tackle all at once, so we try to first get the simple case right. And in the case, for instance, of skin tone ranges, we first focused on portrait images, which have a front-facing face. Then we mastered the production scale, and then we expanded to harder cases and more applications. And last but not least, overall accurate is not synonymous with fair. Biases need to be managed proactively. The system is not going to do that on its own. We don't need to be afraid of sacrificing other metrics when trying to improve fairness. We learned about so many issues when we looked closer at the granular level that we ended up improving the performance for all the groups and did not need to sacrifice other metrics for fairness. Now, inclusive features such as skin tone ranges and hair pattern search make the user experience more inclusive by giving them control on their experience. But we would also like for everyone to feel welcome and represented on Pinterest from the start of their journey. And so to improve user representation, we launched skin tone diversification in various surfaces so that no one has to work harder to find content that is relevant to them. We have diversified search results for beauty and fashion queries, fashion product recommendations in shopping discovery surfaces, and we welcome new users with a diverse initial home feed when they first join Pinterest. Diversification approaches aim at re-ranking the content to make the set of items that is surfaced more diverse by default. One common approach is to boost or discount scores for content that matches a diversity attribute or that is similar to other items above in the ranking. Now, while boosters or discounters are simple to implement, they tend to become tech debt. They are tuned at the time where they are introduced, and then they are forgotten. More boosters get added, and they are not jointly optimized altogether. And so over the past couple of years, our diversification approaches have evolved from greedy re-rankers to multi-objective optimization with determinantal point processes. So we started with simple greedy re-rankers that take as input a list of pins ranked by their utility scores, the pin skin tones, and score thresholds, and re-rank them to produce a diversified ranking. We deployed these simple approaches in various product surfaces, and we saw that they were effective at increasing diversity with neutral to positive impact on utility metrics. However, these simple approaches do not balance diversity and utility, and they do not generalize easily to many different diversity dimensions, and multiple score thresholds are just not scalable. So we evolved diversification to a multi-objective optimization framework that can balance various utility functions and diversity using DPP, determinantal point processes. DPP is a machine-learnable probabilistic model used in physics for repulsion modeling and more recently in recommender systems. DPP is parameterized by a positive semi-definite kernel matrix whose diagonal entries represent the utility of the pin, and the utility score of the pin can be a function of different utilities. And the off-diagonal entries in the matrix represents the similarity between pairs of pins based on diversity features, such as, for instance, the skin tone of the pins. And per this model, the probability of a selected ordering of pins is proportional to the determinant of the kernel submatrix restricted to that subset. It increases with the utility of the selected pins and decreases with the similarity of the pins. And so maximizing that determinant ends up promoting high utility and high diversity pins in the ordering. So I would like to share with you an example parameterization of DPP. So we have a utility matrix, which on its diagonal has a function of the utility scores, a symmetric similarity matrix S, whose entries are similarities between pairs of items and could be computed, for instance, as a function of item embeddings. We have free parameters such as theta that balances the trade-off between utility and diversity, and learnable functions, F and G, that could be learned, for example, using deep neural networks. And the kernel is a matrix that is a Gramian matrix built as the product of these utility and similarity matrices. And with this parameterization, the probability of a subset Y of items is a function of the determinants of the utility and similarity submatrices U and S restricted to the columns and rows in the subset. And the log of this determinant is, as you can see, a weighted sum between a utility term and a diversity term where the parameter theta balances utility and diversity. And I give a more explicit example at the bottom for a toy 2x2 submatrix where the log determinant has this simple formulation. As you can see, the utility functions and the similarity term there. Now, DPP is NP-hard. However, thanks to its submodular property, a DPP solution can be efficiently approximated using a greedy algorithm by greedily selecting the next item to add to the subset such that the incremental determinant is maximized. So this side-by-side is an example for the query short hair in search. On the left, we have the results with the greedy reranker with score thresholds, and on the right, the DPP results. The score thresholds in the greedy reranker limited our diversification attempts, while DPP, with its flexibility, allowed us to generate a set of results that had both high diversity and high utility. Our experiments have showed that DPP can achieve on-par diversity and utility compared with greedy rerankers, but it balances the diversity-utility trade-off in a way that allows to expand the coverage of diversification to more beauty and fashion queries and to multiple diversity dimensions in a scalable manner. In our diversification experiments in various production surfaces that were successfully launched and deployed, we observed gains in diversity metrics with neutral to positive impact on utility metrics. And this suggests that the systems may not be operating at the Pareto frontier between diversity and utility, as we can increase diversity without negatively impacting utility, or sometimes even increase both. Now, if we think a little bit further, we can also envision moving the diversity-utility Pareto frontier. For instance, we understand that diversity at the end of the pipeline is limited by diversity earlier in the pipeline. And so if we can work end-to-end throughout the pipeline, we can help improve the diversity-utility frontier. So I would like to conclude by sharing some recent feedback from pinners. Hearing from pinners and creators that our work is making a positive difference in their lives has been the most encouraging reward for our teams. And so I would like to leave you with a message of hope that change in technology is feasible if one is intentional about it. Thank you.